Welcome back to Reconstructing Relativity. This will be Chapter 6 called Parallel Plane Circular Motion. This is the third mode of constant speed harmonic motion that we'll be looking at. And then we can proceed with other topics in relativity. This is the third of three. So we'll get started. By way of quick review, the first motion we looked at was circular motion in a plane perpendicular to the direction of motion of the particle, which gave us a helical motion of energy through space. And secondly, we looked at radial cyclic motion, which gave us this interesting pattern of energy cycling as a particle moves through space. And notice again that in both of these first two cases, the cycling time for the moving particle is longer than the cycling time for the non-moving particle. And remember also in this case, for radial motion, we saw that when the particle's not moving, the boundary of reflection is circular to get the energy to all come back together harmonically. But for a moving particle, the boundary of reflection has to be elliptical in order for the energy to come back harmonically. Now, the third type of motion we're going to look at, the new motion, is called parallel plane circular motion. So we'll go back to a bug traveling in a circle, or energy traveling in a circle, as the car moves forward, as the particle moves forward. And we'll have the energy circling around in this direction, and we'll see what happens to it and its motion as the particle moves forward. And we'll have the same rules as before. Our little insect bug will be flying always at the same speed through air, representing energy always traveling at the same speed through space. So try and imagine what the motion of this energy might look like as the particle, as the pattern moves forward in this direction. Here are some pictures of the vector triangles in this analysis. And for these pictures, the brown arrow is the motion along the path. So relative to the antenna, the bug is flying a path, always tangent to that path, and that's the brown arrow. But you see the velocity of that relative motion, the brown arrow, changes dramatically when the bug is always flying through the air at the speed of the red arrow, which is c, but there's always air relative to that, which is leftward. So in order to stay on the path while flying in the direction of the red arrow through air, the relative velocity of the bug changes dramatically. So these pictures kind of go around clockwise as the bug goes around clockwise, flying first to the right, then downward, then leftward. So when it's flying leftward, the relative velocity is very large because the bug's flying through the air along the red arrow, but the blue arrow is also to the left, so that makes the relative velocity extremely high. Then as the bug flies upward again around the circle, around this path, then it slows down again, and then as it heads finally at the top back towards the right, its relative velocity will become very small again. So we'll see the whole picture in a second. So here's the results, animated. There's kind of a lot to talk about here, but I'll show this first, and then we'll talk about it a little more. At the left, we've got just a non-moving car, non-moving particle, and the energy within that particle, the bug is the energy, circles around the antenna tip, and in a certain amount of time it goes around twice. At the right, as viewed from the side of the road, we're watching this pattern go past us. We see a bug that's following around the edges of an ellipse as the ellipse is moving to the right. And we notice that the height of the ellipse is twice the width of the ellipse, and that the time of the cycle is twice as slow as the non-moving circling of the circle. So we've got a 2-to-1 height ratio on an ellipse, and we've got a 2-to-1 time slowdown for the cycling time as this pattern moves towards our right with energy circling around it clockwise. Now, why did I pick an ellipse for the moving pattern? Why not stick with a circle? Did I need it to use an ellipse? The answer involves a matter of harmony. Let me explain. This is what's called an oblate spheroid. It's like a sphere, except in one dimension, everything is shorter. So you see the radius A, and then radius C, where C is shorter than A. And every point in this oblate spheroid, the vertical height of this spheroid is shortened by that ratio of C over A. So it's just like a sphere that's been squashed somewhat. So if we take an oblate spheroid, turn it on its axis like this so that the short axis is left to right, we see this relates to all three of the constructive models that we've done so far. The first one, the helical motion, is represented by that red arrow to the left in my picture. The motion of the bug was around a circle, and as the circle moved to the right. In the second one, we had bugs or energy emanating from the center point out to an elliptical boundary as that ellipse moved to the right. And you can see and that the height ratio of the ellipse was R over gamma. In other words, it was twice as high as it was wide for gamma equals 2. And for this third model that we've been using, the other red arrow that starts at the top and goes towards the right, that's applicable here. So that's what we're doing. We're following that path along an ellipse, same height ratio of gamma, following along that ellipse as we go around, as the ellipsoid moves to the right. So here's the thing about harmony. If we put our first analysis with a helix next to the analysis we're doing here, we see that both have 0.866 V over C, in other words, a gamma of 2. We see that compared to just a circling, non-moving pattern, these go around once. Both of these go around once, whereas the circles going around twice. And the timing of both of these is exactly the same. The harmony of those two different motions in the perpendicular plane and the parallel plane tell me that we could send a bug off or energy off in any direction from that tap point around this oblate spheroid, and they would all return back to the top at the same time after one cycle, which would be twice as slow as the non-moving sphere, the cycling time of the non-moving sphere. I haven't done that yet. I haven't proven that. The math would be a lot more difficult to go off at a different angle like that. But I'd bet a week's wages that would be true, that this geometry will give a harmonic return for energy traveling in any direction around it, in a circle or an ellipse around this oblate spheroid. So think about this, meditate on it. I have, and I'm convinced, I hope you are too, from the examples we've seen. If all matter is nothing but energy trapped in a cyclic pattern, and the energy is always moving at speed c through space, then if that pattern is moving through space at speed v, and the pattern of motion of the energy inside is compressed by the ratio gamma in the direction of motion of the particle through space, the cycling rate of that energy will always diminish by ratio gamma also. Think about it. The energy can't sit still, and a cyclic pattern means it comes back to where it started. So in any direction it goes, it's got to return. And whether that's laterally, transverse, or in the direction of particle motion, or against the direction of particle motion, all these effects that we've seen in our three examples will be present. So I'm convinced that this is, we've seen enough to accept those facts. So that's about it for this video. There's just one more thing I want to do. I want to read from my book a chapter-ending paragraph that explains exactly where we are in the overall process, because we're not there yet. All right, here it is. We have started to build a constructive model that underlies the phenomena of relativity, but we are not there yet. We are getting a sense now of what may cause the time dilation and length contraction which scientists measure, but we do not yet have a model which is complete enough to explain the observed measurements of science. We have one major hurdle yet to come. After we master it, we will be able to explain why scientists always measure light to have the same speed regardless of the motion of the reference frame, which is used to make the measurement. If we can get to that point, then we'll be at Einstein's starting point. If we can get there, then the rest of Einstein's derivations of the equations of special relativity will follow. Only this time, we'll have a constructive model which underpins it. We will have a vision in our mind's eye of a physically logical process that supplements the abstract mathematical description. And with that, quick YouTube reminder: like, subscribe, share, all that good stuff, and I'm going to pick some music clip to go out on. When I pick it, I'll put it in there, and we'll hear it. Thanks for watching. Catch you next time.